So our third and final content point is going to be applying the principles of energy conservation and thermodynamics to investigate, describe, and predict efficiency of energy transformations in technological systems. Well, that's a mouthful. We need to figure out first what the laws of thermodynamics are and then how to apply them. There are traditionally 3 laws of thermodynamics. They're up to the 4th law now. Or actually, they call it the 0th law because they realized it was underpinning everything. But the first law is conservation of energy. So energy cannot be created or destroyed in an isolated system. So the total amount of energy in a system cannot change if that system is isolated or closed. You can turn potential energy into kinetic energy, or vice versa. You could turn things into heat energy, although it is very difficult to turn heat energy back into any other types of energy. So you can transform it, but you cannot create or destroy it. The second law is that the entropy of a system is always increasing. Well, what is entropy? That is the amount of disorder in the system. So chaos in the universe. This is why you cannot easily turn heat energy back into another type of energy. It's because that is the entropy. You're creating that disorder when you're making the heat. And you cannot reduce the amount of entropy in the system. You might be thinking, wait a minute. What about a fridge? A fridge reduces the amount of heat, right? Well, have you ever noticed that the fridge has these metal gratings in the back and that you have to leave airflow around that fridge? That's because of this law of thermodynamics. So yes, they have figured out how to take a fridge and use it to cool off the interior. So say keep the inside at 3 degrees Celsius. But if it does that by pumping 2 kilojoules of energy out of the interior, then more than 2 kilojoules of heat energy are going to spew out the back. If we had a perfectly efficient system, which does not exist, then they'd both be 2 kilojoules. This has some waste heat. So that thing you see in movies on a super hot day, when people just open the fridge door and stand in front of it, well, it feels good when you're the one standing right in front of that fridge door. But the cool air that's coming out is overpowered by that extra heat as it keeps trying to pump and pump and pump and pump. So while the space immediately in front of the fridge may be getting cooler, the space in the rest of the area will be getting hotter. This is why when you see air conditioners, air conditioning units are mounted in windows. Because if you're pumping heat in the front, it has to come out the back. So if you have an air conditioner that's not window mounted, you're not cooling anything off, as we may have noticed in certain rooms in Headway. Now the third law of thermodynamics, and the final one that we dealt with in Science 10, is that the energy in a system will approach a limit as the temperature goes to 0 degrees Kelvin. That lower limit is absolute zero. This is the coldest possible temperature. They used to say it's where all atomic motion stops. They stopped saying that for reasons that we'll deal with in Physics 30, when we've discovered that it's impossible to stop all subatomic motion, but it is possible to drive all subatomic particles into the lowest available energy state. And that is what we have at absolute zero. So this was a very quick recap of the concepts that we saw in Science 10 that will then feed into Physics 20 and 30.